Computational. 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 Thinking.
My name is Ryan Griffin, and I am a senior computer science / computer engineer major at North Carolina A&T State University.
My name is Carice Hanson, and I am a junior computer science major at North Carolina A&T State University.
My name is Jamon Goodwin, and I'm a junior computer science major here at North Carolina A&T State University.
Hi, I'm Tiffany Francisque, a junior computer science major at North Carolina A&T.
Hi, my name is Morgan English. I'm a computer engineering major at North Carolina A&T.
So let's look at the first algorithm. The first algorithm is the Ethiopian peasant algorithm. Now this algorithm stores y and z as two integer variables. The first value y is divided by z and divided by 2 or half until the value equals 1. The second value z is doubled for the same number of iterations as performed on the first value. The original algorithm uses the operation 2z or z plus z. These numbers are stored in the second column. For every row in the second column that corresponds with an odd number in the first, add the number in the second column. Together, the sum of the numbers is the product of y and z. The second approach to problem number 1 is the Egyptian multiplication. Now, this algorithm stores y and z as two integer variables similar to the first algorithm. Under the first column, you start with 1 as your first number. These numbers are then doubled each time, or x plus x, until the number is less than or equal to the original number. In the second column, the value is doubled each time, or y plus y. This continues for the same number of iterations as column number 1. These numbers add up to the value of x in the column 1 that are selected. The numbers in column 2 that correspond to the selected numbers in column 1 are then added. The sum of these numbers equals the product of y and z.
3, we're bringing in int x and int n, and if n is 0, then we return a value of 1. Else if n is the product of n divided by 2 is equal to 0, then we return x times x, and n divided by 2. Else we return x times x and n minus 1 divided by 2. Okay, for method 2, we're bringing in x and n, and we're setting the result equal to 1. And we have a while statement. While n is a non-zero, we'll also have an if statement inside of that where first index of n, if that's a non-zero, then the result is a running product of x. Then we'll have n decrement each time. Then we'll end the if statement. We'll have x equal to a running product of x outside of that. Then we'll have n halve itself. And then that's it.
Bet you can't prove it though.
Alright, so let's look at a proof to see that these algorithms really do work. The first proof is for the Ethiopian peasant algorithm. You start with 80 and 15 as your first numbers. Now you would divide 80 by 2 all the way until you get to 1. The second number, 15, is doubled for the same number of iterations in the first column. So it would go from 80, 40, 20, 10, 5, 2, you ignore the remainder, and then 1. In the second column, you start with 15 and you double each time. 30, 60, 120, 240, 480, and 960. Now you look in your first column for the odd numbers. The two odd numbers in this column are 5 and 1. Now, you look at the corresponding numbers in the second column. The numbers that correspond with 5 and 1 are 240 and 960. You then come over and you add to make sure that these two are correct. So 240 plus 960 equals 1200, which is the same as 80 times 15, which also equals 1200. So you know that these two really do work. The second algorithm is the Egyptian multiplication algorithm. Let's use the same numbers to make sure that we're doing it the right way. 80 and 15. And with 80, you start with 1 and you double until you get to the number that is less than or equal to your original number. You then double 15 for the same number of iterations in column number 1. So you start with 80, you have 1, 2, 4, 8, 16, 32, and 64. You then double these starting with 15. 30, 60, 120, 240, 480, and 960. Now you add together the two numbers that equal 80 in the first column, which are 64 and 16. You then check off the numbers that correspond with these. So the number that corresponds with 16 is 240, and the number that corresponds with 64 is 960. When you add these two numbers together, you get 1200, and also, as I said before, when you multiply 80 and 15, you get 1200. So it really does work.
The runtime for both the Ethiopian peasant and the Egyptian multiplication algorithms is both big O of n plus n squared because both of them are so similar.
R divided by Z. For this algorithm, you reverse engineer y equals qz plus r in order to solve for both the quotient q and the remainder r. For the second strategy, y divided by z equals x minus the floor operation of x equals r. You divide by y and z and make the result x. Next, you have to subtract x by the floor operation of x in order to get the remainder r. The floor of x is equal to the quotient of q.
Oh yeah? Well, prove it then.
To prove strategy 1, we will use y equals 50, z equals 3, and q equals 16. Now when we put these numbers in the algorithm, it will go q equals 16, which equals 50 minus r divided by 3, which goes to r equals 50 minus 16 times 3, which equals 48, which also equals 50 minus r, which also equals r equals 50 minus 48, which the remainder would be 2. For strategy 2, we will use the same numbers, but for strategy 2, would be 50 divided by 3, which equals 16.67, which equals x, which we'll have to subtract by 16, which will equal 0.67, which will be the remainder.
The complexity for method 1 is represented algebraically in 4 steps, whereas method 2 is algebraically represented in 3 steps.
Okay. In problem 3, basically it takes two integers, y and z, and passes them to a method that computes what y is when it's raised to the z power.
So for the pseudocode for problem 3, we bring in int x and int n, and if n is 0, then we return a value of 1. Else if n is the product of n divided by 2 is equal to 0, then we return x times x, and n divided by 2. Else we return x times x and n minus 1 divided by 2. Okay, for method 2, we're bringing in x and n, and we're setting the result equal to 1. And we have a while statement. While n is a non-zero, we'll also have an if statement inside of that where first index of n, if that's a non-zero, then the result is a running product of x. Then we'll have n decrement each time. Then we'll end the if statement. We'll have x equal to a running product of x outside of that. Then we'll have n halve itself. And then that's it. So prove it.
For method 1, we have x equals 5 and n equals 2, which means 5 to the second power. So when n is not equal to 0, or when n is equal to 0, then it's just going to return the 5, because 5 to the 0 power is 1. So n is 2, so we divide, but n 2 divided by 2 is 1. So that just means we do 5 times 5, which is 25. So, and for method 2, we have 3 to the 10th power. Right, so 10 is even, so we just do 3 times 3, which is 3 squared, 9. And then we go down and we half the 10 with 5, so 5 is odd, so we do 3 to the 4th power, which is just, at this point is 9, so it's just 9 times 9, which is 81. And then we subtract to get an even number, so n minus 1, which is 5 minus 1, which is 4. So we divide 4 by 2, so 2 is now even. And then we basically double this number, and we have it 81 squared, which is 3 to the 8th power, which is 6,561. And then we divide again, 2 divided by 1, which is 1. And we add 2 to this one, so we get 3 to the 10, which is what we had originally, which is 59,049.
For the complexity of method 1, the runtime is big O of n log n, whereas for method 2, it's log n. So which algorithms did you choose? The first algorithm is straightforward, and it does not require you to use subtraction. This is one less operation that has to be performed. If you have fewer operations, you can save time trying to solve a problem. By saving time, you improve the efficiency of the algorithm. For problem 2, in order to come up with the best answer the most efficient way, strategy 2 should be used. It is a simple, correct, and efficient algorithm that will give you the quotient and remainder in forms that you would see on a calculator. Strategy 1 gives the right answer, however, more is needed to complete the algorithm and more is needed to end up with the final answer. As far as cost efficiency, strategy 2 is the best option here. For problem 3, the best algorithm to choose would be the integer power algorithm because of its runtime. It allows for the numbers to be between any positive range, whereas the second chosen algorithm only allows for there to be a power that is a power of 2.
La, 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 la. Mary, Mary. La, 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 la. Thank you. When I look back over my life, thank you. And all the times you brought me through, thank you. I just want to say, Father.